Good afternoon. I'm Alex Beloyu.
I'm Aaliyah Raven.
I'm Mackenzie Tassiello.
I'm Hanson Liu.
And I'm Vincent Silva.
So the experiment we conducted is regarding the effect of different construction methods of metal oxides on efficiency of dye-sensitized solar cells. So what is currently happening in the community regarding these solar cells? So currently, scientists are looking to improve solar cells in the aspects of efficiency, practicality, and cost, as currently they have many problems. So currently, scientists have been looking into advancements in solar batteries, such as developing molten salt batteries and graphene batteries, creating more wearable solar cells to be used in like electronics and watches, and also creating transparent solar cells.
So why should we care? Well, as you can see in this chart, in recent years, global temperature has been on the rise and it's hit its all-time peak. So the need to switch to renewable energy is more prevalent than ever. So our question that we're trying to answer is how to make an efficient solar cell without silicon. Because the problem with silicon is that it's expensive to fabricate, so the average households cannot afford it. Only around 9% of all households in California even have solar panels, and this needs to change. Dye-sensitized solar cells, like the ones we created, are inexpensive, but they're less efficient. So this research will test many different plausible solutions to find which solar cell has the highest electrical output.
So this is a diagram of our solar cell that we constructed in our lab. So on the white layer here and the white layer here is our glass slides, and there's a thin layer of fluorine-doped tin oxide on top, which serves as the conductive layer. And right over that, over here, is the graphite catalyst, which serves as, it lowers the activation energy for the redox reaction of the iodide electrolyte. And then underneath that is the anthocyanine dye, which underneath that is the metal oxide, which is the semiconductor. And the way the electrons flow is the light passes through the dye and excites an electron, which moves onto the metal oxides through the conductive layer and then goes back through the circuit. Meanwhile, the iodine is undergoing a redox reaction, which allows the electrons to be replaced in the dye that were through the circuit.
Okay, so our experiment primarily focused on metal oxides, and the purpose of these metal oxides, or like the prime purpose, is that it applies a nanoparticle sized like layer over our solar cell, and what that does is it allows for increased absorption, and increased absorption logically results in more electrons being in the circuit and a higher electrical output due to the fact that metal oxides are an integrated layer that trap and transport the photogenerated electrons.
So in our experiment, we tested several different metal oxides, the first being titanium dioxide, also known as TiO2, and it's commonly used in dye-sensitized solar cells. Its large current density, exceptional stability, and low cost make it an ideal material. And the next metal oxide that we tested was magnesium oxide. And magnesium oxide is slightly insulative, which gives it some different properties. It also has a nanopore structure, which increases dye adsorption. And so our last material is zinc oxide. And zinc oxide also has a large surface area like the other metal oxides, as well as a reduced recombination rate, which means more electrons can successfully flow through the circuit. It also has direct electron pathways, which increases the efficiency of the solar cell. So our research question was basically which construction of the metal oxides will produce a higher voltage output on the multimeter. And so we predicted that a solar cell constructed by pre-mixing the MgO and the TiO2 would significantly increase the surface area due to a nanoporous complex that it would form, and this would increase voltage output.
All right, so step one of our experiment, we had to prepare the metal oxide nanoparticles. So we're given the 3 metal oxides in a powder form, and then we measure out 2 grams of them, and then we add acetic acid, which basically turns it into a solution so we can use it to layer it over the solar cell, and we just grind for 15 minutes. After the 15 minutes, we add a drop of Triton X, which similar to the ferrofluids in the oleic acid, it acts as a capping ligand, and what that does, it prevents the nanoparticles from combining and aggregating to become a larger complex, so that they can do what nanoparticles do, increase surface area and all that, and we continue grinding. And then We then layer the solution over our solar cell, which was way harder than it should have been for us. And then we ended up, after we're done, we heat it and cool it so that the solution can dry on the solar cell. During that time, we prepare our dye, and we basically take frozen raspberries and we filter it so that only the juice is left. And we use raspberry dye because we want to absorb the blue light, because that's the lower wavelengths and a higher frequency, which means there will be more energy and possibly more electrical output.
Yeah, for step 4, we took the second slide that hasn't been used yet, and we coated it with a graphite layer, which is used in order to act as a catalyst to lower the activation energy for the iodide redox reaction. And then in step 5, this is where we assembled our solar cell by placing the two plates together and clipping them with binder clips in order to connect the electrodes. And here we added iodine, which acted as the electrolyte for our solar cell, which helped the charge transfer process, where as light was converted to electricity by the dye, it lost an electron and acquired a positive charge, which here the electrolyte then worked to basically replenish the dye and regenerate it. And then for the last step, we tested our solar cell by placing it on a projector, and then we used a multimeter in order to get the millivolts and microamps of that the solar cell was producing.
So after recording our data with the multimeter, you can see that the TiO2 with the MgO layer is significantly higher. It has a higher voltage output, and it's almost twice of the control, which is the TiO2. Also, you can see that the TiO2 with the ZNO layer is slightly lower in voltage output than the TiO2 by itself. And there's basically the same trend for the current, and yeah, the TiO2 with the MgO layer is much higher than the other two. And also the two premixed have little to no current in voltage. So then using the voltage and the current, we calculated power. And as you can see, the TiO2 with the MgO is much higher. And the zinc layer is slightly lower. And so we believe that the reason why the zinc layer had a lower output was because zinc ions would form on the zinc layer. And this would hurt the electron injection, which is basically the emission of electrons from one solid into another. And this would decrease the overall efficiency of the solar cell.
So you might be wondering why MgO yielded the best results. Well, think of it like a ladder effect. Because there are two layers of the metal oxides, the second layer assists the electrons to go to the excited state. So pretty much the excited state is when the electrons are able to go through the circuit. So if MgO is assisting it, then they could go there with less energy. They go from the valence orbital to the conductive orbital and pass through the band gap. It's better to have a smaller band gap because it requires less energy to pass through. Because MgO has a larger band gap and TiO2 has a smaller band gap, they average out. Also, another reason that MgO yielded the best results is that the thin layer of MgO on the TiO2 acts as a barrier for charge recombination. And that's pretty much the time it takes for the electrons to fall back down from the excited state, and that's not what we want in a solar cell because we want all of the electrons to go through the circuit. So if the MgO is a barrier, then it helps solve that recombination problem. And also, the MgO creates nanoporous complex when it's paired with the TiO2, and that's a picture of a nanoporous complex right there. So as you can see, there's more surface area for the dye to cover and more pores for it to go to. So there's more light is able to be absorbed by it.
So the main reason why we think that the mixtures didn't work and that the layers yielded a very much higher result is due to aggregation. So basically, with the metal oxides on their own, they're in their nanoparticle state and size, which gives them their large surface area property. And then when you mix the two together, it's very possible that they clump up together, which is aggregation. And when you aggregate, there's a loss of the nanoparticles, so now they're in the micro level, and there's less surface area due to that. and with less surface area, less dye is absorbed, and then less electrons go through the circuit.
So in conclusion, a solar cell that is layered with TiO2 and a layer of MgO enhances energy conversion efficiency. Now this is what we tested in our research, but Aaliyah is going to tell us some additional experiments that we could further our studies.
So due to the fact that we believe that the recombination rate is the biggest factor in why the MgO is the success, so we want to test the recombination rate with photoluminescent spectroscopy so we can quantify the amount in comparison to the other metal oxides. And next, we believe that also like a human error in our experiment was the production of the nanoparticles, because some nanoparticles when we produced had a more bubbly solution than the others when mixed with the acetic acid. So we wanted to test different ways to make these nanoparticles and see if that affected the output of the current in the solar cell. And lastly, we want to test if layering the metal oxides makes a difference, for example, like with the band gap, and if having the TiO2 on top of the MgO would reduce the reduction rate.
Thank you.
Does anybody have any questions?
Hi. So sorry if I missed this, but so you tried TiO2 by itself as kind of your baseline. Why wouldn't it work if you just had a layer of MgO or a layer of zinc oxide on its own? Why did you have to mix those?
So there's been a lot of recent studies lately that layering them on top of each other work better, and the structure of MgO does not work as well by itself, and it needs a supplement metal oxide. So rather than testing, we also did not have enough time to test all of them. So rather than testing just MgO and just CNO, we decided to test both to see which layer would work better.
Thanks.
We did a good job.
Yes. I agree. Hi, Zach.
How's it going, guys? So you guys use glass with a thin conductive layer for your solar cell. How come you guys don't use something else that maybe conducts better, like copper or something traditionally used in a wire? Why do you use glass?
Oh, we use glass, sorry, because we need a clear structure for the light to pass through, because if the light isn't passing through, then the electrons and the dye aren't getting excited, and then the solar cell just won't work.
Very good.
All right. We don't have any other questions. Thank you.
Let's go.